In this problem, we're going to solve for the equations of motion for a block on a movable inclined plane. That is to say, this not only can the block move down the incline, but the incline itself can move back and forth. We're going to solve it using the Lagrangian. This is advantageous because Lagrangian, if we can find the Lagrangian itself, we can plug it into Lagrange's equation, and the process is much simpler than the ordinary Newtonian physics we ordinarily use. So, to start, we find the Lagrangian first. We notice that the kinetic energy, is going to be 1/2 mass of the incline, the incline's speed, which will be in the I prime direction, I hat direction, along the x coordinate. So we'll write x dot squared. The block on the incline will be more complicated. It is moving both down the incline and along with the incline as the incline moves. It means we have to add both those velocities together. So we have 1/2 little m and the dot product of x dot I hat plus x prime e theta hat. That's an x dot, by the way. And I'll dot it with itself. X dot I hat plus x prime dot e theta hat. This gives us 1/2 capital M x dot squared plus dot these two, straightforward, 1/2 M x dot squared. Dot product of those two, straightforward, 1/2 M x prime dot. The cross product of these two, both magnitudes times the cosine of the angle between them. You remember your definition of the dot product. That means we can write for this one and for this one, we can write 1/2 times 2 M x dot x prime dot cosine of the angle between them, which in this case is simply cosine theta. The potential is going to be minus m g sine theta x prime, where the vertical distance is x prime sine theta. Gives us this vertical distance. Thus, if we do t minus v, we have our total Lagrangian. Now the next step is to plug this into Lagrange's equation. Notice we have to treat x and x prime separately. They are separate variables. So, if we evaluate x first, then we take the partial derivative with regards to x dot, which means we don't pay attention to x or x prime or x dot prime, just x dot. So we take the derivative, and the interesting thing to note right here, of course, we set up the derivative to take, and the partial makes it easy because we don't have to worry about the other variables. We just ignore them. And since there is no x in the equation, the partial derivative with regards to x gives us 0. So we're left with the time derivative of this quantity equals 0, meaning this does not change in time. No matter what it is, it doesn't change. So the time derivative of it is 0. This is called a constant of the motion. Constant of motion. Very important. Things like this make problems much, much easier to solve in real life. Now, once we take the actual derivative, we will get little m x double dot plus, and you should be following along with this yourself. Can't learn physics if you don't do physics. So just follow along, and if you get confused, just think it through. Okay, this equation gives us this. This is our first second-order equation. We will have 2 of them, because we also have to do x prime. Now, we'll follow through this in the same way. We will evaluate the derivative. Now, in this case, will we get a constant of the motion again? We don't always get them, and they're very handy when we do. In fact, all of your conserved quantities in physics are really just that, constants of the motion. In this case, no, we don't get a constant of the motion, because this does not equal 0, it equals that. So, evaluating and simplifying, we get x double dot prime minus x double dot cosine theta minus g sine theta equals 0. Now we have 2 constants of 2 second-order equations. Now we can use these 2 in a little bit of algebra. We won't need anything else, just a bit of algebra. Substitution. We can solve for what x double dot and x prime double dot are. So we can understand the equation of the acceleration of each of those. In order to do that, I'll first simplify this one and get, switch pens, x double dot prime equals g sine theta plus x double dot cosine. Notice we did bad. No, we're correct. We left an m out right there. We can divide all sides by lowercase m. It cancels out. And this is all here is all true. Once we have this, we can substitute it into this equation. If we solve and simplify, we get x prime equals, let's pull it over here. We get this equation right here. With some simplification, we can take this one, plug it in right here, that substitution, substitute this for x double dot, and we get, after some simplifying, this formula right here. In other words, we have solved this entire equation with just a little bit of running through Lagrange's equation once we had the Lagrangian. This is what makes the Lagrangian so advantageous.